Well, thank you all of you for being here. Alain is present here. He's president of Molket SAS, a member of QEDC and QIC, founder of Quantalan Sasu, and Alan Quant LLC, offering management consulting and AI services. He's an advisory member at North America Technical Institute, Virginia, USA. Also, he's a Qiskit advocate, IEE senior member, society affiliate of the American Chemical Society, member of the American Physical Society, and the Quantum Security and Defense Working Group. He is co-author of Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit code. With 30 years of experience in enterprise transformation, he holds a diploma as an Ingénieur Civil des Mines from École des Mines de Saint-Étienne, France. Okay, it's up to you, Alain.
Thank you for having me. It's the first time I make a presentation for Argentina, so it's an honor to be here. Sample-based quantum diagonalization. I present as Molket SAS, and as mentioned, I'm also a Qiskit advocate, but this presentation I make as president of Molket SAS. Okay, so let's move on to the next slide. Okay, hold on. Hope I can just bear with me. So somehow, okay, I will just reshare. Okay, just bear with me. Okay, so this is the introduction. So you can see the first page, the cover of the book I co-authored with Dr. Alain. And by the way, there is on GitHub, there is a repository which is public by Pact Publishing, and I made a fork where I maintain as best as I can the Jupyter notebooks, the Jupyter notebooks which contain the examples of the book. So effectively, you can have the executable version of my book, Jupyter notebooks, which contain all the for those who have purchased the book, they're entitled to download the complete version with all the texts, the images, and the formulas in LaTeX, and of course the exercises, the illustrations in Python and Qiskit code. Okay, let's move on. So I hope you can see, yes. So today I'm going to present an overview of the so-called sample-based quantum diagonalization algorithm, and I will illustrate this with Jupyter notebooks, which are published on my public GitHub. So Alain Chance SQD_Alain. As you can see on this screenshot, there is a bunch of molecules which where I've successfully run this algorithm. Okay, so this is the agenda for my presentation. So first of all, I will scope this presentation within the quantum-centric supercomputing, then move on to SQD, and then share with you two very important use cases by IBM, and then we'll go into a demo. So quantum-centric supercomputing is a term which has been coined by IBM, but it's not limited to IBM quantum devices, because IBM and Pascal have a partnership, and together they aim to they have defined a what they mean by quantum-centric supercomputing. So that covers the superconducting loops, the qubits that IBM Quantum have used, and also with Pascal, the neutral atoms. So quantum-centric supercomputing is the future of high-performance computing, HPC, and is the way to achieve near-term quantum advantage, at least hopefully, in chemistry, material science, and a number of other scientific applications. So, as you would expect by the definition, a quantum-centric supercomputer is comprised of quantum processing units, GPUs, and CPUs. Right? So I've provided the reference of this definition. Okay. Now, sample-based quantum diagonalization. There are several definitions. I prefer this one. It's initially SQD is a chemistry simulation technique. Now, it has been recently extended to cover other fields, provided the Hamiltonian satisfies certain conditions. But my presentation is focused on the initial use of SQD, which is the chemistry simulation technique. So as you see on the left-hand side, there is a workflow. It starts on the top, create LUCG, stands for local UCG, which is a quantum circuit. But this is not created as a quantum fluctuation. It is based on knowledge of chemistry, and there is a package known as FFSIM, which also uses the PySCF Python package. So classical chemistry is leveraged at the very beginning to basically help set up a quantum circuit, an ansatz, which is supposed to have to be able to model the molecular system. Okay, and I won't go into details. There is a bibliography at the end which explains the terminology, in particular CCSD. So there is classical quantum chemistry at the very beginning. A quantum circuit is created, and it is from this quantum circuit that samples of possible electronic configuration are extracted in the form of bit strings. And so with the currently available QPUs, the sampling is done on a noisy distribution. And so you see, then the next step is to run the said quantum circuit, collect configuration dictionary. And the key part, which makes SQD different from other methods like variational quantum eigensolver, VQE, is that there is an iterative correction, which is done entirely on the classical side. And so it is hoped that this technique has been shown actually on a few use cases, that for a large enough noisy quantum computer, and this is what we have today, up to 156 qubits, at least with the free plan, with low enough error rates, that this approach has the potential to perform more efficiently than classical approximation methods. So we shall see in more details. So this depicts the steps. So the first on the left-hand side, it's just a single run of a quantum circuit, but of course that means many measurements. But unlike VQE, this is the quantum computer is only use one. The quantum processing only occurs once. That's the big difference with the other variational, with so-called variational quantum algorithms. And on the right-hand side, you see the post-processing. So this is where it is innovative. That is to say, there is a a number of batches of subsamples from the noisy probability distribution are created, and then ideally in parallel. So you see on the diagram on the right hand side, there are several eigensolver from S1 Sk. So for these batches, basically it's diagonalization classical, but the key is that it is done on these subsamples, which means it is computationally feasible. So because it would be beyond the capabilities even of the most powerful HPC, high performance computer, to directly diagonalize the full matrix. The SQD approach breaks up the this big impossible to diagonalize matrix into smaller ones, and then they are somehow combined, and then there is a clever error recovery procedure, which is similar to error mitigation, but I would call it smart error mitigation because it takes into account the knowledge of the molecular system. And in chemistry, it's the symmetries. So that makes it possible to fix errors from the noisy output distribution. And this process is repeated a number of times, and it has been shown, and this is what I will illustrate, that this iterative procedure does converge to the very good, very well to the in that case the lowest energy. Okay, so the minimum ground state energy, which is of interest. Okay, let's move on. So why does it matter? So this is an example, a very interesting use case, a collaboration between IBM, Cleveland Clinic, and Riken University in Japan, and they have access to the most powerful supercomputer in the world, known as Fugaku. And together, they have managed to simulate with SQD. So it's SQD within the context of quantum-centric supercomputing. Okay, they managed to simulate the ground state dissociation of N2, nitrogen, but also the clusters 2Fe, 2S, and 4Fe, 4S. And on the left-hand side, we see that for the 4Fe, 4S simulation, it would be impossible to achieve that with today's QPU and using the variational quantum eigensolver. So there is a presentation by Antonio Meza-Capo, and I give the link, which explains in more details why it is hopeless to simulate this iron sulfur cluster with VQE. 3 million years, you see. I mean, it's just impossible. With fault-tolerant QPUs, which hopefully we will get by 2029, that's within the IBM plan, with a better algorithm, quantum phase estimation, it would still require 13 days continuous. So it seems beyond what could be reasonably achieved, because it means 13 days continuous. And you imagine if there is anything happening, if the competition is stopped before the end of these 13 days, then we have to start all over again, because once there is a measurement, the quantum state is lost. It's projected. So that seems not that doesn't seem feasible realistically. But the good news is what has been achieved. within a quantum-centric supercomputing framework, so with the most powerful supercomputer in the world, and a Heron superconducting quantum processor, QPU. With SQD, that simulation has been achieved in 2 hours. Okay. Okay. This is another example, and this one I will illustrate with a kind of a demo. This time it's a partnership, a collaboration between Lockheed Martin and IBM. They have applied the SQD method, again within a quantum-centric supercomputing framework, to simulate the dissociation of the ground state triplet and also the first excited single states of the CH2 molecules. So it's methylene. Okay. And their study is relevant both for interstellar and combustion chemistry. So the plume which is ejected from a reactor of a plane, typically. So on the left-hand side, we see what's interesting is that when this was achieved, they only had access to a 52 qubits QPU, whereas today we have access with the free plan from IBM to IBM Fez and IBM Marrakesh, and they both have 156 qubits. So imagine nowadays anyone can, many people can access the free plan and we run this simulation with accessing a much more powerful quantum processing units. So I will explain in more details what happened, but basically we have two different flavors, if you want, of the single molecules, they keep swapping between one another. There is the singlet and triplet, which we'll see that in more details very soon. So why does it matter? So on the left-hand side, you see a diagram which represents a number of computations. So horizontally, you see the length of the bond between a carbon atom and a hydrogen atom in the CH2 molecule. And vertically, you see the energy, so it's negative. So it goes from minus 38.70 to minus 39.05. And what happens, and there are 3 different methods: SQD, CCSD, SCI. CCSD is very popular classical quantum chemistry simulation method. SCI is the most accurate one, but requires many more resources. And SQD is the algorithm we're interested in. And what is amazing is that SQD actually you see the yellow and red points basically are superimposed, which is very good news because it means that SQD really matches in terms of accuracy the best classical method, which is known as SCI. And the rectangle, the box, indicates where there is a transition between the singlet and triplet states. You see the triplets are represented by dots, while the singlet is like three legs, and you see these they intersect, and this is where it matters both for interstellar and for combustion chemistry to accurately model what's going on when there is an exchange of state. Okay, so let's move on. So now I'm going to go into a bit more details. So the single state, we can model it with the so-called 6 -31G, basis set, a basis set. And again, there is a glossary at the end of my presentation. Is simply a set of functions in quantum chemistry. People for many years. I mean, quantum chemistry has existed long before quantum computing was popular. And so researchers have devised a number of different basis set, a number of different functions that model more or less accurately the behavior of molecules. And 631 is a popular basis set. So you see on the right-hand side that for the singlet, there are two different scenarios, two different and the arrows going up and down, they represent the spin up and spin down states of the electrons. And you see that in the singlet state, so it's at the top on the right hand side of the diagram, they are in the same orbital. Okay. And whereas at the bottom, you see the two arrows are up and they are in different orbitals. So this is the difference between the singlet and triplet states. Now I would like to show the which I'll see whether you can see my my screen. We can switch to the okay. So great. So now you can see my it's on GitHub. You can access it. It's a public. You can see at the top the URL, so you can actually anyone who participate in this event can access my public GitHub, the repository sqd_Alain, and access the sub folder sh2 singlet. Okay. Now there you can see the initial configuration, and I've developed a so-called Gradio interface, which makes it very easy to run. And we see in that example that the basis set is 6-31G, as I mentioned. The job ID is the ID of a job which has been previously run, which is of interest because it means that you run. It might take a few minutes to run, and the ability of reusing a job ID means that you can try several different variants of the error recovery based on the same probability distribution that came out of this run. So there is also a possibility to load a BitTorrent file. Now, the compute exact energy just is an option to compute or not compute the exact energy. Classically, bearing in mind sometimes for some molecules, this computation cannot be achieved because there is not enough memory. So you untick this if you run into that kind of issue. Now, in the there is a box run on QPU, and then it opens a drop-down next box, and it automatically presents the list of IBM backends which you are entitled to use. Okay. And there is an option to plot a gate map. Here, the chemical configuration, the atomic configuration, is entered, and then a few things. But what makes it really comfortable, easy, is that basically you can load the this is saved into a JSON file, so you can load it, and in the on my repository, you see what I've run is saved into a JSON file, so it can be loaded, and then you can run the computation. So maybe I could show you what I've done just a few minutes ago. I think I can show you that. Yes. So this is the actual, this is my Jupyter notebook running in Ubuntu under Windows. So this is okay. And what you see is that so I will just share with you. So this is the Gradio interface. So this has been entered, and the result is shown here. So in this, we see that the SQD energy is very close to the one computed classically. And in this second window, we see the so-called energy and occupancy plot. So I will just explain. So this is the energy, and this is the iteration. So it shows that just after 5 iterations, we had reached the accuracy, which is called a chemical accuracy, which is 1 millihartry, so 10 to the minus 3, this dotted red line. So after just 5 iterations, we have reached the chemical accuracy, and then we can improve on that. And on the right-hand side, you see the average occupancy per spatial orbital. So we can see that so there are, you see, 2, 4, 6 electrons, which are basically occupying the same spatial orbital, and they are those two, they occupy different orbitals. So so this is for the singlet. Okay. So now we can have a look. So this is again my own Jupyter notebooks. We can check. We can see the same with the triplet. And in the case of the triplet, yeah. So you see it's a different file, so it has been saved and can be loaded again. So the so this is the so if I go back to my presentation, okay, so actually, yeah, somehow I in my run I use the triplet instead of the singlet. So the singlet, the all the 8 electrons share the same. Well, there are 2 for each orbital. Okay, whereas for the triplet, it is what I just shared. Okay, so so this is what I wanted to share with you. So I've shared with you a few definitions for those of you who are not familiar with quantum chemistry. The basis set, as I said, is a collection of mathematical functions. So there are basically a few like STO 3G, which is the minimal basis set. So it's the one which is used to perform computations when memory is limited. 631G is the next level in terms of accuracy. It is much more accurate than STO 3G. And there are other bases which are even more accurate than 631G, but require more memory. Okay. I also share an extended bibliography. Okay. So I'm now available. If you want, we can just run a simulation, and while it is running, I'm open to questions. So let's see this one. We can see. Okay, so I'm sharing the Jupyter notebook. So I will reset everything and start running. So I will just close this. Okay, so it's running, And the only thing which the notebook does is start the gradual interface. So I'm going to close this one. I'm now starting this one, and this is the gradual interface. So I can load the configuration. So you see, it's definitely the singlet. Okay. You see here, if I click on Run on QPU, there is this drop-down list box, and you see I'm entitled to use IBM Fez, IBM Torino, IBM Marrakesh. So I'll choose IBM Fez, and the rest has been set up properly. So I just need to save the configuration and run. And while it is running, I can go back to my Jupyter Notebook, and you see, so there is kind of a log which illustrates the configuration. It is running on IBM Fez. However, I've run out of I've used up all the 10 minutes, so I will at some stage I will cancel the job. But you see, it starts exploiting the performing. It performs a classical computation, the CCSD calculation. The exact energy is computed, but it's for the purpose of benchmarking, comparing the result obtained with the SQD. Now you see the number of qubits, 26, so it's way beyond what can be simulated with Qiskit Air simulator on a laptop. Typically on a laptop, you can go up to 22 qubits if you have got, like me, 32 gigabytes of memory. But so that means it can only be run on an actual QPU, or I will explain. First of all, so you see the initial layout, and I will show you. So this is a new feature. I hope you can see. Yes, you can see. This is very recent. This is something I learned from attending the IBM Quantum Developer Conference just last week in Atlanta. So there is a new function which automatically works out the best layout given the number of qubits and the molecular the molecules. So this has been computed automatically. Okay. We can also have a peek at the quantum circuit. So it's quite. So this is the ansatz. This is the LUCG quantum circuit, which has been set up with knowledge of the classical modeling, if you want, of the molecule. Okay. So let's go back there. So where are we now? Okay. So you can see that the job has been submitted, and it is queued. Now what I will do is I will because I've run out of so I will just cancel the job. Okay, I will cancel it. I hope in a few days I will be able to run this, and you see what happens in the back to the Jupyter Notebook. There is a message: error retrieving job result, unable to retrieve result. A job was cancelled. So this is exactly what I've done. But as a fallback, it generates. So that's very interesting. Since we cannot run a quantum circuit, we can nevertheless generate a uniform distribution, which is of course of much lower quality than the noisy probability distribution we would expect by running the quantum circuit, the ansatz. But the error recovery procedure is so efficient that for small enough molecules, it turns out that even with a uniform distribution, which is generated with a function which is provided by the Qiskit add-on, it's actually possible to run the self constant configuration recovery procedure and to end with a good result. So it takes a number of minutes, so we won't wait until the end, but I just wanted to show you. So it's very easy. Just run this Jupyter Notebook. It automatically opens the Gradio interface. Then you can simply load a configuration that has been saved previously and run. And you see in the Jupyter Notebook the way it executes. So I think that concludes my presentation, and I'm now open to questions, if any.
Thank you very much, Alain. Does anyone have any question? Well, I will start, Alain. Which do you think right now are the main bottlenecks that we have, let's say, putting this information in a quantum computer and retrieving, let's say, a good mark for the ground state energy of a molecule?
So first of all, the big advantage of quantum chemistry is that we can start from first principles. So with quantum chemistry simulation, we don't have the issue of the bottleneck of loading classical data into a quantum register in the first place. So that's really convenient because it means all we need is to have a good ansatz, so a quantum circuit that represents the behavior of the molecular system. It turns out that for years now, researchers have come up with very good ansatz. And the LUCG is a good compromise. So it's very well explained by Antonio Mezzacapo in his video, the video I mentioned in the presentation. So that's very important because yeah, we need to sample from a quantum circuit, and it does matter. The quantum circuit represents the molecular system. What happens is that very similar to classical quantum chemistry, and again in quantum chemistry, what that means is from first principle. Okay, doesn't necessarily mean that quantum chemistry requires quantum computing. Okay, but classical quantum chemistry, the complexity of the computation grows exponentially given the number of particles, the number of electrons, and so unfortunately, even though in theory we have a very accurate way of making computations, we run into an impossible trade-off because in chemistry it's very important to have an accuracy of the milliarity. And there are methods to simplify the calculation, but then we lose the accuracy. Now it turns out that, and this is something we can experiment with my Jupyter notebooks. When you use a more accurate model, so for example, you go from STO 3G to 631G and then to CC PV and that kind of stuff, the number of qubits it's not a surprise, increases, but it remains reasonable. You see, in a simulation with 631G for CH2 singlet, we had 26 qubits, which is very reasonable, and so the number of qubits is not an issue, and the depth is beyond the depth of the quantum circuit is beyond what can be achieved without any error on today's quantum processing units, but the recovery procedure is very efficient. So, in a nutshell, today, at least for SQD and quantum chemistry, I think now is the time to run experiments because I'm eager to try on the latest QPUs made available for the free plan because it's Heron 2. As IBM Torino, which was the best one available just a few weeks ago, is Heron release R1, whereas the IBM Fez and IBM Marrakesh, it's Heron R2, which have better fidelity. And so for those who have access to a paid plan, they could access IBM Boston, which was made available to the participants of the Quantum Developer Conference. IBM Boston is Heron Release 3, it's even better quality. So in terms of fidelity, we are talking about, I think, Aaron, IBM Boston, it's 1 point something by 10 to the minus 3. And it's much better than IBM Torino, and it is much better than the quantum processing device, which the researchers used, the collaboration between IBM and Rockwell. So I'd say at the moment, the limit is more the creativity of the developers, because we have new hardware, we have software which is very promising. So now is the time to experiment and see how far we can go. Does
Okay,
that answer
great.
you? Yeah.
So also the choice of the basis set is also critical as the ansatz, no?
Yes, indeed, because
Mm.
there is like a zoo of basis sets. There are
Yeah, right
websites
now.
which there
Yeah.
are literally hundreds of basis sets. Okay, and but so far, what has been used for that kind of simulation is the most popular one, STOS 3G 631G. I think the authors used one CCPV-DZ. And yeah, so the answer is really important, because both for the classical computation requires lots of memory. Sometimes it's so much memory you can only run that on a supercomputer. I mean, it's way beyond what can be done on a laptop. And on the quantum computing side, yes, the number of qubits, it is directly related to the choice of basis set. And the more accurate it is, the larger number of qubits, and also the depth of the circuit. So yes, but it is, I would say, open to researchers to accurately find out, to experiment and determine what can be achieved today. I think anyone can be at the forefront of this research, because it's only since a few days ago that these latest resources were made available. Yeah.
Okay, great. Thank you very much for the answer. I don't know if there is another question. Okay.
Yeah, please go ahead if there is anyone who wants to ask a question. Otherwise, after the you can always reach out to me on my LinkedIn profile, or if you are a Qiskit advocate or Qiskit enthusiast, you can reach out to me on the Qiskit Discord, and I will be happy to satisfy your curiosity about this topic. Thank you for your attention.
Okay, thank you very much, Alain, for having you here and telling about quantum chemistry and this algorithm.
Thank you.
Thank you very much. See you soon.
Thank you.